Okay, our next section is going to be covering stars. Stars are going to be defined as large celestial bodies composed of gas that emit light. The sun is going to be the closest star to Earth, and we know that stars are going to form from clouds of dust and gas known as nebula, and they will go through different stages throughout their life as they age. And we'll take a look at the life cycle later on in this section of notes. In order to measure the distance from Earth to these faraway stars and galaxies, we had to come up with a new measurement. This is known as a light year. This light year is going to be equal to the distance that light can travel in 1 year, which is roughly 9.5 trillion kilometers, or in miles, that would be roughly 6 trillion miles. So stars we talked about are going to be forming from these clouds of dust and gas, and they are powered by what are known as nuclear fusion reactions. What happens is stars are made up of these hot, dense clouds of hydrogen and helium gases, and they're under extreme pressure. And so when particles of a star start to fuse, they will release energy into their surroundings. And so that energy will move slowly through the layers of the cloud and dust that make up the stars. And there's two different methods in which these layers will actually move. There's convection, which is going to be where our hot gases will move upward or away from the center. And as they do so, they're going to cool the gases as they get closer to the outer space. And then as they cool, they will sink back towards the core. The second one is going to be radiation. So atoms are going to absorb energy, transfer it into the random directions, and what you'll find is that atoms near the surface will radiate energy into space, and that's where we'll get light from our stars from. Here's a picture of the different layers of a star. This is looking at our sun, and you can see that there's several different layers, and each one of these layers has a different temperature rating to it. You can see by far the sun is going to be the most hot layer, which has over 15 million Kelvin. And then the outermost layer is going to be our photosphere, which is only about 6,000 Kelvin. So it's very hot at the core of the star and roughly cooler towards the edges of the star. Astronomers did not really begin to learn about the nature of stars and what makes up or causes them to radiate light until we came up with the telescope. Thus, once we had the telescopes, we were able to determine what actually makes a star and its brightness. The brightness of a star depends on three things. The first is going to be the temperature at which the gases of the star burn. So the temperature is going to be key in that. The second is going to be the size of the star. How big or how small is that star? And then the third is what is the distance from Earth? Our brightest star in the sky is going to be Sirius. It is the closest star to Earth other than our sun, and it is 8.7 light years away. How we learn about stars is by studying their energy. Stars produce a whole range of electromagnetic radiation, anywhere from X-rays all the way out to radio waves. And what we know is our atmosphere will block some of those wavelengths. So in order to study these stars, we'll actually use telescopes in space in order to pick up this wider range of spectrum of light and energy that these stars radiate. We also know that the color of a star is going to be related to its temperature. Hotter stars will have shorter wavelengths. That means they're going to be closer to the blue end of the spectrum, while cooler stars will have longer wavelengths, which will look more red in this case, or have more reddish color in that spectrum. Hot stars will emit more energy than cold stars, and thus they will burn brighter. If you look at the spectral lines of the stars, this is actually where we can pick up the gases that make up that star. Each element, once again, produces its unique pattern of spectral lines. We talked about this earlier in our chemistry unit, and these lines will actually be used to determine the elements that make up those stars. So you can see here the star spectral line is going to be on the top, and the bottom is the spectral lines for hydrogen. They match up with several of those lines, so we can say that this star will have some hydrogen gas in it. I mentioned earlier that stars will go through different stages of a life cycle. Very similar to us, they will be born, they will go through different stages of development, and then they'll eventually die off. Our sun is formed from a cloud of gas and dust, and the sun currently is being balanced in one of those middle stages of life by two forces. There's an inward force and an outward force. The outward force is going to be fusion. Fusion reactions are taking place that produces the outward force, radiates heat and light, and then gravity pulls those molecules back down towards the core in order to reheat those atoms of the gas that make up our sun. In order to show where a star is at on its life cycle, we use what is known as the HR diagram. This shows the different stages a star will go through throughout its life, and if it's found at the diagonal line, this is known as a main sequence star. And currently, our sun is following this pattern of a main sequence star as well. So you can see here, this is the HR diagram. That middle line or that diagonal, that's our main sequence star, and our sun is located right here within that main sequence. So it's more towards the end of its lifetime as it starts to cool off. However, it's still within that main sequence pattern. I mentioned earlier that Sirius is one of the brighter stars, or the brightest star that we see from Earth. Sirius is actually going to be classified as a white dwarf, and thus is not going to be part of the main sequence pattern. So scientists believe that our sun will continue to follow this main sequence pattern and eventually become a red giant before it dies off. What's going to happen in order for that to take place is as the fusion reactions start to slow down, what will happen to our sun is that the outer layers of the sun will continue to expand and our sun will form into a red giant. A red giant is going to be classified by its large, reddish, late stage of its life cycle. And what will take place is that the sun will actually run out of the helium in its outer layers as those continue to expand, and eventually they will leave the sun's orbit. What will be left behind after the red giant is going to be a white dwarf. A white dwarf is going to be a smaller, hotter, dim star that is the leftover center of an old star. And so eventually we'll go to a red giant and then maybe a white dwarf after that. Supergiants are also going to be located on the HR diagram. Supergiant stars, what can happen with them is they can actually form supernovas. A massive star, they evolve faster, they develop hotter cores, and they create heavier elements through the fusion process. And so what eventually happens is those cores will collapse and then they will explode outward into what is known as a supernova. So a supernova is going to be that gigantic explosion which comes from a massive star collapsing upon itself and throwing its outer layers out into space. A black hole is going to be an object so massive and dense that not even light can escape its gravity. And this is what's going to happen as there's going to be a leftover core of a star that has collapsed upon itself, and it can form into one of these black holes. So you can see here, all stars start out as stellar nebula, or clouds of gas and dust, and they can develop into our average stars. And this is where our sun is currently located. Our sun then will develop into a red giant. It will then lose its outer layers and develop into a white dwarf. Bigger stars can develop into red supergiants, and then they will go through the supernova, which then can develop into a black